Hello students, welcome to EPG Pathshala. I am Dr. P.K. Aluwalia from Physics Department, Himachal Pradesh University, Shimla. Today we are going to talk on module Equilibrium, Thermodynamic Parameters and Response Functions from paper Statistical Mechanics. So students, let us see what we are going to learn in this module. We will try to understand and analyze the way term equilibrium is used in thermodynamics and statistical mechanics. To understand the importance of long observation time while describing equilibrium, distinguish between extensive and intensive parameters, and that these are homogeneous functions of order 1 and 0 respectively. See how intensive parameters are related to extensive parameters. Understand relaxation time in the context of a perturbed system going to equilibrium. Learn about the concept of generalized forces, generalized coordinates, and response functions. This module on equilibrium, thermodynamic parameters, and response functions of statistical mechanics has been developed for postgraduate level as per the following subtopics: meaning of equilibrium vis-a-vis observation time, extensive and intensive parameters, thermodynamic equilibrium, three types of equilibrium, statistical equilibrium and relaxation time, non-equilibrium and irreversible processes, generalized forces and response functions. Let us try to understand meaning of equilibrium. State of equilibrium and non-equilibrium are intuitively the most subtle concepts in the study of thermodynamics and statistical mechanics. It is one of the very fundamental questions to pose, that when can we say that a system is in equilibrium and when it is not. In this module, we shall explore the meaning of equilibrium as applied to thermodynamics and statistical mechanics in the context of macroscopic systems encountered in the physical world. So, first, let us try to understand what is state of a macroscopic system. Indeed, thermodynamic equilibrium is a macroscopic phenomena. It has no meaning in the case of an isolated particle. A macroscopic system consists of a large number of particles, say n, very much greater than 1, under a given physical condition in a particular equilibrium state described by various parameters such as pressure P, temperature T, magnetic field H, etc., which can be tuned from outside as external conditions. This table which you are looking at describes state of matter in equilibrium at specified external conditions. If the external conditions change, the system may go from one state of equilibrium to another. For example, when the external condition is 373 degrees Kelvin at normal pressure, water boils. But if the temperature changes to 273 degrees Kelvin at normal pressure, water solidifies. In the case of helium, at 2.17 degrees Kelvin at normal pressure, it behaves like a superfluid. Iron below 1043 degrees Kelvin at normal pressure behaves like a ferromagnet. A gas of rubidium atoms at 170 nanokelvins at normal pressure shows Bose-Einstein condensate. Lead below 7.19 degrees Kelvin at normal pressure becomes a superconductor. In this e-course on statistical mechanics, we are going to talk about statistical mechanics at equilibrium. It will be worth appreciating the meaning of this equilibrium. An intuitive and plausible way to understand the meaning of equilibrium is with relation to observation time. It will be nice to look at a few examples. Let us take the case of warm water in a thermos flask. It remains warm over a long period of time, implying that if you record the temperature of water over a period of an hour, you will find the temperature has not changed. Pour the same water in a cup. For a couple of minutes, you may find that water remains at the same temperature. But if you wait for half an hour, you will find that water has cooled down and it is not the same state when it was poured into the cup. Also, take a cup of water at room temperature. You can notice it has a definite volume, and this volume stays the same after a few hours. However, if you observe the level of water, say, after 3 or 4 days, you will notice that maybe half of water has evaporated. This has happened because evaporation caused removal of the water molecules from the cup, though temperature may have stayed the same. Therefore, one can conclude that equilibrium has a meaning for a given system provided observation time is not too large. By keeping water in a thermos flask, you have been able to prolong the state of equilibrium through isolation, making cooling of water a very slow process. In simple words, we can say that if we observe a system over a short enough time that its state remains unchanged, system is in a state of equilibrium. It must be underlined here that no system is in a state of what we call absolute equilibrium, that is, in equilibrium over an infinite period of observation time. Absolute equilibrium is in a sense idealization, which does not normally happen in reality because no system can be practically made completely isolated. Before we further discuss the meaning of thermodynamic equilibrium, it will be nice to understand the meaning of thermodynamical parameters. For example, temperature, pressure, volume, entropy, etc., which may be needed to identify for a system in equilibrium. In fact, by specifying these parameters, we specify the state of system. Broadly, thermodynamical parameters can be classified into two types: extensive parameters and intensive parameters. Let us try to understand the meaning of extensive parameters. Extensive parameters, as the name suggests, these are the parameters whose value depends on the extent of the system, or simply put, the size of the system. These parameters are directly proportional to the size of the system. If size of the system becomes alpha times the original size, the corresponding parameter should also become alpha times the original value. There is another way of visualizing the meaning of an extensive parameter. Imagine we have a macroscopic system having two parts as shown in the figure 1. If an extensive thermodynamic parameter of the composite system is y, and of part 1 and 2 are respectively y1 and y2, then y is said to be extensive if y is equal to y1 plus y2. For example, mass, volume, entropy, energy are all extensive parameters. Therefore, an extensive parameter of a system in equilibrium has a value which is sum of the values of each part of the system. Now we will try to understand what are intensive parameters. Intensive parameters are thermodynamical parameters of a macroscopic system in equilibrium which are independent of the size of the system. With reference to the figure which you are looking at, if y is an intensive parameter, then y is equal to y1 is equal to y2 with respect to the two parts. For example, such intensive parameters include temperature, pressure, and chemical potential. It is also worth noting that an extensive parameter and an intensive parameter both are homogeneous functions respectively of first degree and 0 degree of the variables on which it depends. For example, if f, which is dependent on x1, x2, x3 and so on up to xn, is a homogeneous function of order n, it means f with its independent variables scaled by lambda, that is x1 taken as lambda x1, x2 taken as lambda x2, x3 taken as lambda x3 and so on, xn taken as lambda xn, it will become equal to lambda raised to power n as a function of x1, x2, x3 and so on up to xn. By checking the degree of thermodynamic parameters, we can keep an eye on their intensive and extensive nature. Euler's theorem, which is a very interesting theorem from mathematics, helps us to provide thermodynamical relationship via a very interesting property of homogeneous functions of degree n. Euler's theorem states that if there is a function f of x1, x2, x3 so on up to xn, and if it is a homogeneous function of degree n, then n times function of x1, x2, x3 so on up to xn can be written as equal to x1 multiplied by partial derivative of f with respect to x1 plus x2 multiplied by partial derivative of f with respect to x2 plus x3 multiplied by partial derivative of f with respect to x3 and so on up to xn multiplied by partial derivative of f with respect to xn. We must appreciate this theorem is very useful in arriving at thermodynamical relations, which we will see later in modules. Entropy S, which is an extensive parameter, is a homogeneous function of first degree of internal energy U, the volume V, and the quantity of matter represented by number of particles in the system N of the system. Therefore, ds is equal to du delta S by delta U at constant V and N plus dV into delta S upon delta V at constant U and N plus dN into delta S by delta N at constant V and U. By inverting the functional form of S, we can also write internal energy U, which is also an extensive parameter and is a homogeneous function of degree 1 of the entropy S, the volume V, and the quantity of matter represented by number of particles in the system N of the system. Therefore, du is equal to ds, partial derivative of u with respect to S at constant V and constant N, plus dV, partial derivative of u with respect to V at constant S and constant N, plus dN multiplied by partial derivative of u with respect to N at constant V and constant S. On comparison of the equations 1 and 2 with well-known expression for conservation of energy in thermodynamics, we can write du is equal to Tds minus Pdv plus mu dN, where first term on the right hand side corresponds to increase in heat, second term corresponds to mechanical work done, and the third one corresponds to chemical work done respectively. From this equation, we can get the following definition of intensive parameters in terms of entropy and internal energy respectively. For example, we find reciprocal of the temperature is equal to partial derivative of S with respect to U at constant V and N. pressure divided by temperature is equal to partial derivative of S with respect to V at constant U and constant N. Chemical potential mu divided by temperature T is equal to minus partial derivative of S with respect to N at constant V and constant U. Also, in terms of internal energy, we see that temperature T is equal to partial derivative of U with respect to S at constant V and constant N. Pressure P is equal to minus of partial derivative of U with respect to V at constant S and constant N. And chemical potential mu is equal to partial derivative of U with respect to N at constant V and constant S. The relationships enunciated in equation 4 and equation 5 are very useful relations which can be used later to arrive at interesting results once entropy or internal energy are known to us. For example, knowing equation of state PV is equal to N kVT and internal energy is equal to 3 by 2 N Boltzmann constant multiplied by temperature of the classical ideal gas, we can write entropic forms of the equation of state and internal energy and hence classical entropy of the monatomic gas and deduce functional form of entropy as a function of internal energy U, volume V and number of particles N. For a macroscopic system to be in thermodynamic equilibrium, in fact, it has to be in three types of equilibrium. First, thermoequilibrium, second, mechanical equilibrium, third, chemical equilibrium. Thermal equilibrium means that every part of the system and the surroundings are not experiencing any change in temperature with time. Mechanical equilibrium means that net external forces and net external torques acting on the system are zero. Chemical equilibrium means that there are no chemical reactions taking place in the system and the concentration of the constituent particles of the system is constant with respect to time. Thermal equilibrium in fact is related with constancy of temperature. Mechanical equilibrium means constancy of pressure. Chemical equilibrium means constancy of chemical potential. Let us try to understand what is the meaning of statistical equilibrium vis-a-vis relaxation time. If a macroscopic system and its macroscopic subparts have macroscopic physical quantities equal to their mean values, the system is in statistical equilibrium. In other words, if a macroscopic system is observed over a long enough time, then for most part of the observation time, it will be in a state of statistical equilibrium. It is also possible that a macroscopic system may, by some external interactions, at a given instant of time is not in a statistical equilibrium. It will, after the disturbance ceases to act, shall come back to the state of equilibrium. This time which it takes to come back to the state of equilibrium is known as relaxation time. Once we have understood the meaning of equilibrium processes, it will be worth understanding the meaning of non-equilibrium and irreversible processes. When a system is not in equilibrium, there is some action from outside the system. Sometimes we wonder that most of the phenomena which we see around us are not in a state of thermodynamic equilibrium. For example, weather pattern. If we analyze closely, we shall find that the cause of weather patterns is from outside the earth in the form of solar radiations. Also, energy flows out of the earth. As long as this exchange of energy shall continue, system will not be in a state of equilibrium. When by applying a potential difference across a wire current flows, we have created a state of non-equilibrium. As long as the system is in this state of energy input, the non-equilibrium process will last. Another simple example that brings in non-equilibrium is the case of two cups of water at different temperatures brought in thermal contact with each other. In this case, system shall evolve from a state of non-equilibrium to an equilibrium, and the two cups of water will come to the same temperature. Now, if we desire that the water in the two cups comes back to their original temperatures, it will not be possible because the process is irreversible. In this course, we are only interested in systems in equilibrium. Now, let us try to appreciate the link between generalized forces and response function. Whenever an external force is applied on a macroscopic system, it shows a response to it and do appropriate work on the body. The response to the external force is a measurable quantity and is described by what we call a response function. Such forces are many and are appropriately called generalized forces. Each generalized force has a corresponding conjugate variable parameter. Change in the value of generalized parameter multiplied by generalized force gives the work done on the system. The table which you are going to see now gives the list of generalized forces and coordinates of interest to us in thermodynamics and statistical mechanics. In this table, we have given generalized forces and generalized coordinates corresponding to each generalized force, which we may come across in future in the study of statistical mechanics. For example, corresponding to mechanical force F, if we treat it as a generalized force, the generalized coordinate or the conjugate parameter or variable corresponding to this generalized force is the position x, and the work done is F into dx. In the case of generalized force external magnetic field H, the generalized coordinate is magnetic moment m, and work done is H into dm. For the generalized force called torque, represented by Greek letter eta, the generalized coordinate is angle, represented by the Greek letter theta, and work done is eta into d theta. Looking at pressure P as a generalized force, we find that the corresponding generalized coordinate or variable is volume V, and the work done is minus P into dV. Treating chemical potential mu as a generalized force, the corresponding generalized coordinate is in terms of number of particles n, and the work done is mu into dn. Temperature T as generalized force, entropy turns out to be the generalized coordinate, and the work done is T into ds. It is interesting to note that entropy is a generalized coordinate which is a response to temperature in a collective way of small scale microscopic changes. Do remember the generalized coordinates are large scale coordinates or thermodynamic coordinates. From the third column in the table 2, it is clear that each of the generalized forces causes a change in the corresponding generalized coordinate. Thus, chemical potential is a generalized force which causes a change in the number of particles in the system. Temperature is a generalized force which causes a change in the entropy of the system. Magnetic field is a generalized force which causes a change in the magnetic moment m of the system. Pressure P is a generalized force which causes the change in volume of the system. So students, let us now summarize what we have learnt in this module. In this module, we have learnt the meaning of equilibrium for a macroscopic system, and that it may involve thermal equilibrium or mechanical equilibrium or chemical equilibrium or all the three. That observation time decides whether we are looking at a system in state of equilibrium or not. Large observation time may allow system to change the state. That Thermodynamic parameters are of two types, extensive and intensive. Extensive parameters are homogeneous functions of order 1 and intensive parameters are homogeneous functions of order 0. Therefore, extensive parameters scale with size, whereas intensive parameters are independent of the size of the system. The meaning of relaxation time vis-a-vis the transition of a perturbed system into equilibrium state once the perturbation is removed. We have also learned the notion of irreversible process in the transition of a system from non-equilibrium system. The concept of generalized forces and corresponding generalized coordinates encountered in thermodynamics related to the response of the system in terms of measurable quantities was also learned. Thank you.